Hi everybody, my name is Jenny. I, along with Rich Brown, who was wondering about earlier, am one of the admission tutors here at Durham in the science department. I am a geophysicist. I'm a lecturer on the geophysics course, and I'm going to tell you a little bit about earth sciences in general as a subject, and about Durham specifically itself and what it's like to study earth sciences here with us. Okay, so what are we going to do? We're going to have this presentation, which will be 30-40 minutes long, which will talk about the other department, earth sciences, careers. We'll have a little interlude from Isabel, who's sitting over there, who is one of our current students, who'll tell you what it's like for her, so you don't have to take my word for it. We'll also, afterwards, we can look about all this stuff, as I just said. Rich will also come back and offer people tours of the department if anyone's interested to see some of our teaching rooms, some of the labs and things like that. Right, so, as I said at the start of the last one, I would never, in my lecture, sit and talk at people for 40 minutes, because it's really boring and no one can concentrate for that long. And so what I like to do is intersperse some interaction and things to keep people awake, and ask all my students questions. So before we start, the first slide is called What is Earth Sciences? So I want to know, what do you guys think Earth Sciences is? You're all here because for some reason or other you want to study Earth Sciences, or you'll maybe be interested in studying. So what is Earth Sciences? What do you think? There's no wrong answers here. I want to know what you think Earth Sciences is. What kind of things does it cover? What kind of stuff are we actually talking about here? Any ideas? Any thoughts? Yeah?
Maybe the study of like earth processes.
The study of earth processes. That's a really interesting answer. Anyone else? You can also employ my lecture tactic of pointing at people at random. What do you think earth sciences is? Yeah?
Sort of like physical geography, but more applied and more in detail about the Earth and the systems that happen within it.
Yeah, sort of like physical geography. Some of the stuff you might cover in physical geography at A level, yeah, we'd count that as earth sciences, and yeah, we might do it, maybe approach some of it quite quantitatively. Any other thoughts? What would you say earth sciences is? Or what does it mean for you? What kind of thing are you interested in earth sciences?
I'd say it's probably the processes which form and shape the earth that we have today and that influence the future.
Yeah, that's great. How did the processes that happened in the past get us to the planet we have now, and what's going to happen with it in the future? That's a really interesting question. Right, so there's no right answer to this, right? Earth sciences is a really broad subject. I like to think of it as applied science, okay? Any science you like. It's taking that science and applying it to questions about our planet that we live on, okay? So that could be interested in maths, physics, chemistry, geography, biology, computing, statistics, any of those things. There's a flavor of earth science for you. If you're interested in physics, maybe you'll become a geophysicist, thinking about how to apply physics to understand questions about the earth. Maybe you'll become a geochemist, looking at the chemistry of water, gases, rocks, to answer questions about how volcanoes work, how the atmosphere works, how it was like in the past. There's a flavor for everyone depending on your interests. And the other important thing to remember is it's also a major field, a major global employer and a major field of study in general. So you take a degree in earth sciences, you're very employable at the end of it. So what do we study as earth sciences? Some of you have talked about some of this stuff already. We think about the genesis, so how things form, how it started, how it forms, and how it functions today, our planet. And everything on it, okay? That's, there's so much stuff that covers. We can think about oceans, continents, mountains, volcanoes, earthquakes, the deep structure of the earth, what's going on thousands of kilometers down beneath our feet. That's what I study. I'm interested in the earth's deep mantle, how it moves and convects over time and affects the processes we see on the earth's surface. But we have lots of people here who are interested in all sorts of different things. The study of life, paleontology, like the study of life on other planets, astrobiology, and the study of volcanoes. There's all sorts of things. It's a really wide subject. We also focus on our relationship with the planet. Okay, so it's not just about, oh, we have this lovely planet, how does it work, let's try and understand it. Let's also try and think about how we interact with it. How do humans impact the planet in terms of climate change, pollution? We have a lot of impact on our environment. How can we minimize that? How can we do the things that we need to without damaging things more than we have to? How how do we extract the energy and resources that the planet provides for us in a sustainable way? So Earth scientists protect humans from the planet. We have natural hazards, things like volcanoes, earthquakes, tsunamis. We'll study these things, understand them, and think about ways to mitigate that hazard and that risk. But we also think about how we can protect the planet that we live on from us, from the impacts that we have on it in terms of climate change and pollution. So given the world and the place that we're currently in, there's never been a more important time to be an earth scientist, right? We obviously have climate change. This is a big thing. It's happening. We need to mitigate our impact. We also need to learn to adapt to the changes in our planet, to the more extreme weather events and disasters and things like that. The other thing that people don't often think about is if we want to have a green energy revolution, if we want to transition away from fossil fuels, what do we need to do that? One of the things we need is rare earth elements, metals. We need to extract that from the ground, okay? If you want battery technology, if you want solar panels, you need the resources to do that from mining, right? We still need mining, but we want to be able to do that now in a really careful way so we can minimize our impact and the negative impacts that can have while getting what we need from the planet that it provides. Okay, so earth science is big topic, loads of different things. I can't even mention them all because there's so many different things. So again, I'd like to ask you, these are big questions. What kind of stuff do you think that we use? What data could we collect? What tools do you think we use to answer some of these questions? Again, this is something I like to do with my students because if you already know all this stuff, I'm not going to spend lots of time telling you about it. That would be very patronizing. What kind of stuff have you heard of already, or what do you think that we could use? What data can we collect? What tools can we use to analyze that data? Have a few minutes, chat amongst yourselves, have a think, let me know what you think. And I'll tell you a little bit about what we can do in this department.
This big ship and the time to manage it. So yeah, now I actually do it a few days ago. We learned about it at the start of the year when it wasn't thought to be a successful project and that is.
Okay, you've had a little while to start thinking about this. Have you got any ideas? What kind of things, what kind of data could we collect, or what kind of tools could we use to answer questions about the Earth? Anyone got any thoughts? You guys think you look like you're having an interesting conversation.
Would you like talk about the climate data, so like sea level rise and temperature and stuff?
Sure. We could take measurements of data of temperature changes, sea level rise changes, things about changing climate that we can take from ice cores and stuff like that. That's a really good point. Any other thoughts? What can't you say?
Oh, we talk about ice cores and CO2.
Yeah? Can measure the CO2, or we can measure things in the air bubbles that are caught in ice. We can also look at things like fossils, microfossils that can tell us about changing the oxygen isotope ratios in microfossils that can tell us about past climate. Any other thoughts? What do you guys at the back think? Any ideas? What kind of stuff could we use?
Just looking at like monitoring volcanoes and looking at like the levels of different gases that
Great. Monitoring volcanoes, great one. We could monitor the gases that volcanoes are emitting. We could monitor them using instruments called seismometers, which measure the shaking of the ground, measure little earthquakes that can tell us about magma moving underground. Any other thoughts? What do you think?
Not entirely sure.
No, that's fine. I mean, you're here to learn, right? You're here to get an idea of what this is about. That's okay too. Again, there's loads of stuff, right? And I don't even really have time to talk about it all, but I'm going to give you a few examples. One thing that we do is as some of you have mentioned, we collect data from the real world. We go out into the world and we collect data. And that can be all sorts of things. If you're on the environmental course, that might mean going out and taking water samples from rivers to look at pollution levels. It might mean, if you're in the geology course, going out and looking at rocks in the field. Okay, looking at the rocks, mapping them out, thinking about their orientation, and thinking about what was the environment like when these things formed? What has happened over the history of the Earth to get them to the orientation and the distribution that they're in today? What does that tell us about the Earth in the past? If you're on the geophysics course, that might mean going out with instruments like magnetometers, or this is me in Iceland, varying seismometers to measure volcanoes and earthquakes and things like that. So we go out into the world and we collect data about it. We also stay here and use things like remotely sensed data. Maybe we download data that's collected remotely from things like satellites. So this is what's called an INSAR image, which measures ground deformation from satellites. This is satellite collected magnetic data over the UK, and this is LiDAR data from a drone survey looking at detailed topography over a region. So we collect remotely sensed data as well. We might undertake geochemical analysis. We might have gone out into the field and collected our gases, our water, our rocks, whatever it is that we are collecting and we think can answer a question for this. Take it back to the lab and think about its chemical composition, its isotopic composition. And we have lots of labs here to do that, and that might answer questions about river pollution, but it might answer questions about what the magma is like in a volcanic system and what that means for the eruptive style. Okay? So there's all sorts of different tools. Some people in the department work on what's called analog experiments. What that means is that when we have something like a volcano, so anything in the Earth, it's a very complicated system that's hard to understand. We can simplify that down to a very basic model that we can make in our laboratories. Okay? And we can try and reproduce this kind of things that we see in the Earth and understand it because we've got a control of our model and model it with physical parameters and maths to try and improve our understanding of these complex systems. We can use computational and numerical modeling. This is a model of mantle convection. Okay? How has the mantle, how is it moving and flowing over time? Now, in our planet today, we only get a snapshot of what it's like right now. Okay, or maybe if we're very lucky, we might have 100-year timescales at the very most, 1,000 years if you're very lucky, depending on what data you look at. What we want to know about is, what did it look like when it first formed? How did we get to where we are now, and what's it going to look like moving forward? To do that, we need numerical models to predict changes over long timescales. This is a global scale model. The example here is a smaller scale model of the capability of the ground to produce geothermal heat. Right? So if you want to know if it's viable to sink a well and produce energy from geothermal heat, how much money would that cost? Can you go deep enough? What's the temperature difference at depth? You need models to try and quantify that. And if you want to build computational numerical models, you need maths and you need computing. So those are tools and skills that we teach here in the department that allows our students to do that. Often the data set that we're looking at are huge. The Earth is a big place and we can collect a lot of data. For example, I'm a seismologist, so I take earthquake data. Now let's imagine I have one seismometer that's going to measure the ground shaking. It measures the shaking of the ground at 200 samples per second. Okay, and I might have data there for 5 years. And I don't have just one seismometer, I might have 20 in a network that I'm using to monitor one small part of Iceland. What if I wanted to study the world? The data sets are huge and they become bigger and bigger every year. And so we're looking at ways of using machine learning, artificial intelligence to handle those big data sets. We might want to look at statistical analysis to reveal patterns in the geospatial data, the geographical variation in the data that we see. We might want to look at things in really, really, really high resolution. We might use things like scanning electron microscopy, I can never say it, X-ray tomography to look at microfossils at really small scales, or understand how rocks are changing and fracturing when we put them under stress, to understand how earthquakes work. Right? So we have all of these different tools that we can introduce our students to and teach you about to answer those big questions that we talked about at the beginning. Okay, so Earth Sciences, I obviously think it's a really cool subject. I hope you guys do too. Why do we think you should come here to study it with us? So before I start harping on about all the things why I think Durham is great, what I'd like to hear about is what is important for you to know about? When you're thinking about what university to go to, what's important to you? What factors feed into that decision? Okay, have a little while, have a think. There's also these forms, if you want to, you can fill them out to give us some feedback. But I want to know about what's important to you, okay? And then I can tell you things that are relevant or not. Have a think. Again, there's no wrong answers here. This is your opinion.
It's just what's important is just getting a job at university. Then good reputation, good university. Yeah, exactly. Just end of the day.
Research.
What are you saying?
Not really. It's sort of good that when you get saved, it may not be much worse. But there's quite a lot of scientists you can probably do that change.
Stuff. I really didn't realise this.
What are the differences between earth sciences and physical geography?
That's a very good question. In this university, it's the modules that you can take, you can study. We do have overlap. We have some modules that the geography department offers on our earth science courses and vice versa. But it's just content. So I guess the physical geography guide will be focusing quite on surface processes, so sedimentology, rivers, things like that, glaciers.
Yeah.
We cover that stuff as well. But we also do climate, atmospheres, the deep earth, solid earth structure, large scale planetary stuff. So I was going to say less superficial? Less surface focused stuff.
Yeah.
But you can go to the geography department and ask them.
Yeah.
They probably have a very different answer.
Yeah.
I would have thought. But we have overlap with the departments.
Yeah.
Okay, so we've had a few minutes. What do you guys think? What kind of things are factoring into your decision of what university to choose or what courses you're interested in? Any ideas? Yeah?
The flexibility of it along with biology.
Okay, flexibility. Right, so depending on which modules you can choose across departments and following your own interests maybe, even as they evolve and change as you're introduced to new content. That's a really important one. We'll get onto that. Anything else? Yeah?
The availability of modules which suit my interests.
Right. What can we offer you to study, and is it in line with the things you're interested in? That's a really good point. Yeah?
Are the facilities that the university has?
Right, the facilities, not just of the department, but of the wider university, right? You're not here just to learn, much as I would like that to be the case. You're also interested in, making friends, joining societies, having support while you're here. That's really important too. And while I'm going to be focusing on our department, obviously there's lots of information at the open day from the colleges and the central admissions team, which can tell you all about the extra stuff beyond just taught things. Anyone else? When I was choosing university, one of the important factors for me was how far away it was from my parents. Further the better. And that's fine too, right? This is going to be somewhere where you want to live for the next 3 to maybe 4 years of your life. So the place itself is important too. Okay, so it's important you take the time to have a look around Durham and see if you like it and you can see yourself living here as well. Okay, so maybe I'm going to cover some of the things that are important to you. If there's anything that I don't, you can just come and ask me afterwards, or ask some of the student ambassadors. We have sitting at the back in blue, because they can tell you what it's like to actually be a student. Right, so I'm going to highlight the things that I think are good about our department. Maybe they appeal to you, maybe they don't. This is things that we're proud of. So we have really nice teaching facilities. We have these lovely big rooms, these lovely big screens. We have lots of equipment. Some of it's out on the side there. We've got geophysics equipment. We've got some environmental science equipment. We've got lovely big labs so we can do research. And some of our third and fourth year students who do research projects with us will get to go into those labs and make some measurements, do some real research there. We have a really friendly department. I mean, that's my perception of it anyway. We're not huge. Well, we're not tiny, but we're reasonably small. There's 34 members of academic staff. And what that means is you really get to know us when we're teaching your modules. We have an open door policy, which means you can come and ask us. If you don't understand something in a lecture, or you go away after and you're like, no, I don't know what on earth Jenny was talking about, you can find me in my office and just ask me, or send me an email if you don't want to come and ask me directly. We have technical and support staff to facilitate our research and our teaching. We've got lots of research students here as well. So we've got like PhD students, that's what I'm looking for, postdoctoral researchers. There's lots of people beyond just the lecturers you interact with who are doing active research in the department. We've got about 260 undergraduate students across 4 years, so the class sizes aren't huge. It varies depending on what modules you study. In first year, lots of the modules are taken by everyone, so they're quite big. By quite big, it's not that big. It's like 80 to 100 max. And as you go through your degree and you get more specialized, the class sizes get smaller and smaller. The field geophysics course that I teach in second year this year had 16 people on it, which is quite small. And you had, on that course we had 3 staff members and a PhD student demonstrator. So the staff to student ratio is amazing. And we get to know you, and like I know everybody in the class, and hopefully they know me by the end of it as well. And this is a really, really important one. We have a dedicated student support staff, right? And our department has been ranked #1 in the country for support and administration. And our teaching learning manager, Janice, who all the students seem to love, got an award this year for excellence in student academic support. That might sound a bit boring, and hopefully this is not something that's going to be relevant to you, but if for any reason you have any trouble, for any reason during your degree, we've got an amazing support team to help you with that in whatever way you need, So that's really important, actually. We're part of the Russell Group of universities, which means we're very research focused and we're recognized for that. We rank pretty highly in these ranking systems, which are pretty subjective, but if that's important to you, we rank highly globally and within the UK for the things that we teach. Another thing that we're really proud of is that we got this year, I think, our Athena Swan Silver Award. If this is not something you heard of before, it's an award for recognizing and promoting gender equality in science. So that's something we're pretty proud of. In general, we place a lot of value in our department of making it welcoming for everyone. Okay, so it doesn't matter if you're a mature student or you're an international student. We don't care where you come from. We want everybody to feel welcome and included. And we have a bunch of groups within the department that work to try and improve that and make that happen every day. Okay, and to make improvements when we get feedback from students, staff, support staff, anyone within the department. Here we have the first generation scholars, which are there to support students who are maybe the first people in their family to come to university, so maybe it's a little bit more of an unknown experience for them. We have a group looking at part of an international program on unlearning racism in geosciences. We've got our Equality, Diversity, Inclusivity Committee, which has members from across the department, students, staff, technical support staff, and everybody is welcome to come along and participate. So there's lots of ways that we're trying to do that and recognize that and keep improving on that as we go forward. So, if you wanted to come study with us, what could you choose? We have a bunch of different subjects on offer, which I'll go into a little bit more detail of before telling you what we need from you. Okay? So, we have environmental geoscience. So if you want to, I actually went to one of the environmental geoscientists this morning and said, what is that? What does that actually mean, environmental geoscience? And she said to me, it's the interaction between spheres. Okay? So the hydrosphere, the biosphere, the geosphere, the atmosphere, the cryosphere, which is ice and things like this. So how do all of those systems, how do they work and how do they interact with each other? Okay, so it's quite focused on interactions and processes. And that might be looking at hydrology, climate, monitoring environmental management, things like that, thinking about sustainability. And you could go on to work for environmental consultancies, looking at remediating pollution and things like that. The energy sector, geotechnical or geoengineering consultancies. We have our geophysics degree, my favourite obviously, where we are thinking about applying physics directly to understand problems. So this is quite a quantitative degree. There's emphasis on training in mathematics and computing and using those really useful tools to understand earth science problems. Using geophysical equipment like the things we have over there to understand the subsurface of the earth, but also the overarching physics, the magnetic field, the gravitational field, what's going on deep inside, how heat flows, all sorts of things that are relevant to those kind of questions. And that can lead you on to, something general, like looking at data science, thinking about calculating hazard and risk, again working for geotechnical consultancies, engineering consultancies, working in the water or the energy sector, really anything where you do quantitative analysis of data. We have a climate science degree where you can really focus on climate, sustainability, environmental resources and oceans and things like that. And we have the classic geology degree where you're interested in rocks, but also the processes and things that those rocks physically represent. So volcanic systems, igneous systems, natural resources, paleontology, earth structure, structural geology, all sorts of different things. And we have what we call our geoscience degree stream. So the geoscience degree, so lots of these degrees, I should say, have this little symbol at the bottom. It says Geological Society. That means they are accredited. That means the Geological Society has looked at the modules we taught and said, yep, I think that makes a good geologist or geophysicist or climate scientist. Thumbs up. We have no evidence that being accredited or not affects employability at all. But if you want to go on to become, say, a chartered geologist, it makes things a little bit easier. You can still do that if you get an unaccredited degree, it just takes a little bit longer. But that's something that you can get if you do, say, geology or geophysics or environmental geoscience. But if you want to do the geoscience degree, that is one where you get to pick whatever modules you want as you go through. So as your interests evolve, you can pick things that are of interest to you. It might mean that your degree is not accredited because the Geological Society says you have to do X, Y, and Z in your degree to become accredited. You might not have done all of those things because you picked the things that were of interest to you, but you get to follow your interests. We also offer, so those are all 3-year undergraduate degrees. We also offer a 4-year undergraduate master's degree. So this means you stay on with us for an extra year after you've focused on one of those streams. And in your final year, half of the year is just undertaking a research project. And the other half is really focused on independent learning and taking you out and thinking about applying your skills. And that might mean studying things like earth sciences into industry, where you work with industrial partners on real problems, going to looking at science communication, discussing earth sciences into schools, things like that. So there's a lot of different choice depending on your interests. What do we require if you want to come and study these with us? The grades are varied depending on what you want to look at. Most of the things we're asking for AAB. If you want to come and do the master's course, you need 3 A's. If you want to do natural sciences, which is where you pick modules across multiple departments, multiple science departments, including ourselves. We offer this, but you could do things in physics, you could do things in chemistry, you can pick and choose. That's got a higher entry requirement, A star, 2 A's. Of those 3 A levels you get, or equivalents, we would like you to have at least 2 sciences. Now what we mean by science is very, very broad. Science could be the classics, chemistry, physics, biology, geology, if you're lucky enough to study that at school, but also maths, further maths, geography, economics, and biology or psychology. That's an either or. The only additional requirement is if you want to take the geophysics course, because it's quite quantitative, we would like you to already have A-level maths. For the others, you don't need it, because we will teach you maths and computing a little bit, introduction, see if you like it when you come in. Anything else that's important here? No, those are the key things. Lots of different options. That's the important stuff. So, you say you can study a degree here. What is it actually like? What's the logistics? How does it work? We have a flexible module system, so you can choose what subjects you want to study each year. As I said, some are required because of the accreditation of the course, but there's always options every year where you get to pick things that you're interested in. The teaching builds year on year, So things you learn in first year will be expanded on in second year. The assessment is very varied. Some modules are entirely coursework based, some modules are entirely examinable. Some are based on assessment in the field, from going out and doing stuff in the field. There's a lot of contact time. We have, yes, a lot of contact time every week. Teaching generally takes place in 3-hour slots, which sounds very intimidating, but what it actually translates to is you come in here, the way I run my lectures, because every lecturer does it differently. We're told you have 3-hour slots. Teach people. The way I like to run my lectures, and many staff do, is to have the first hour where I teach content. We have a lecture, we have, with some interactions, you don't have to sit there for an hour. And then following that hour of you learning something new, you get to apply that knowledge in a practical. Okay, and that might mean looking down a microscope and identifying things, or looking at fossils, or looking at rocks, or it might mean doing some exercise and applying the things you've just learned to real data. We have residential field trips. We also run tutorials, and these cover skills that we think it's really important you have that you wouldn't get in terms of the content that we teach. Okay, so these cover things like how to read academic papers, how to write scientifically, how to write a good CV, or how to do a good presentation. Really, really important things that are going to be useful to you in your scientific career and in life in general, that we can help you with. You also have an academic advisor. So that's a member of staff who meets with you once a term throughout your whole degree, and gets to know you and understand what you're doing, where you're going. And because we know you and we know what you've done and how you're doing, we can help you decide what you want to do, choose modules in the future. And by the end, as I'm currently doing for my third years, I'm the person writing references for them, because I know what they've studied all the way through, and I know how they've done. And I know enough about them to say, this person is a real go-getter. They went and studied things in other departments and whatever, because I know them, because I've met them throughout their whole degree. And in your third and fourth year, you will do a research dissertation project that will be supervised by a member of staff. So the module choices follow these very scary-looking flow diagrams. There's a whole bunch of them laid out over there, which shows you, depending on which degree stream you choose, what modules you can do. Some of them are compulsory, which are these ones shown in blue, and some are optional, which are the ones shown in grey. You usually get to choose 6 per year. We started offering half modules in third year, so staff can teach their research interests a little bit more. So that means we get new exciting modules like astrobiology and earthquake source waves, and Arctic climates, because staff want to teach about their own research. It's very exciting. But you can mix and match, especially if you pick the geoscience degree. The other ones have more compulsory modules. The third and fourth year, as I said, have a dissertation component. In the third year, that will be your final year if you're on a BSc program, it's a third of your year. If you do the geology undergraduate, it will be a mapping project. That means you go out for 6 weeks to a location somewhere in the world, and you will make a map. You will walk around, identify the rocks, and make a map, and understand what those rocks are doing in 3 dimensions, and think about what they tell you about the geological history of that location. If you're not on the geology stream, it means you do a research project, and that will be dependent on what stream you're doing. Some examples: seismic noise in the time of coronavirus. That's one I offered last year, looking at monitoring human activity, were people keeping to lockdowns or not, by looking at seismometers, look at ground motion. You might be looking at environmental things, developing methods to test for acid mine drainage remediation, looking at pollutions in river systems. There's lots of staff doing lots of different things. There's lots of options that you get to pick what you want to work on. The department subsidises this, so if you do geological mapping, you get £650 towards your expenses. And if you do any of the other courses that might include some field work, like collecting samples, we'll offer you £250 to support your field work. Occasionally, because these are real research projects offered by our research staff, if they go really, really well, they can turn into published work and get published in journals. And there's a couple of examples out over there of dissertations and papers that have resulted from them. Maybe there was some good initial work from the student, and the staff member took it forward and they became an author on the paper that was eventually published. The dissertation is really important. It's an independent one. It goes on your CV and it says, I know how to write a high quality level scientific report. I can work independently, and I can think for myself. It's really, really important. In third year, this is a third of your year. In fourth year, it's half your year, so you'll do another research project. We can go into even more depth. Okay, a big thing that we want to emphasize is field studies. Obviously, we have field trips and stuff, and field studies are an important thing, collecting data in the real world. However, it's not for everyone, right? I will ask for a show of hands. Do you consider yourself an outdoorsy person? Yeah? Hands up. Does anyone consider themselves not an outdoorsy person? It's really interesting. Exactly the same last time. It doesn't matter. Either or, right? Some people love field trips, and that's great. You get to go out and be outside. Some people hate them. Standing in the rain and the mud, I definitely had times where I was like, why am I here? It doesn't matter, because we need people who are good at different things and enjoy different things. And we like to give experience of fieldwork, but also indirect data collection, right? Remote sensing and things like that. Everybody does fieldwork in first year, right? Even if people have never done it before, we like to give them a taste, see if you like it. If you've never done fieldwork, if you've never done much outdoorsy stuff before, we provide support, right? We'll tell you all about the details of how it's going to work, what you'll need. We'll give you support to get all that stuff in place, and where you can find it, and what you can expect. So it's not too stressful. But if you get beyond first year and you think, God, I hate fieldwork, that's fine. If you're taking the geoscience degree stream, then you can pick to never do a fieldwork again if you don't want to, right? It's an option. If for any reason you can't do fieldwork for a practical or physical reason, we also offer virtual field trips. These were all developed during COVID, and what it means is that if you can't go, you can get a similar experience with these very cool interactive things where you fly to house tops and look around and see stuff. So we can provide an equivalent experience if it's not possible for you, for whatever reason. Right, so the field trips that we currently have on offer, as of now, we have trips to the northeast of England in first year. In second year, there's the northwest Scotland. There's a couple in the Lake District, Cumbria, South Lakes, Spain for the geologists, and then there's some optional field trips which you will or won't take depending on what modules you study. In year 3, Tenerife, Alps, there's an optional field trip to California in the fourth year. Every compulsory field trip, which are needed for accreditation on certain degrees, is free. You do not have to pay for it. You have to pay for your own food. Fair enough, right? But we will cover the costs for any compulsory field trip. If it's optional, we'll ask for a small contribution of it's never more than 150, 200 pounds-ish. Okay, so it should be minimal. It should be affordable. If that provides any accessibility issue for anyone, we can find ways to, hardship funds and things like that. We can find the money to support people. Should never be a barrier. Okay, you might look at this and think, okay, other universities have a lot more international field trips. This looks applicable at all. There's quite a lot of these in the UK. We did that on purpose because we're thinking about our environmental impact, right? We have a no-fly degree pathway. If you take the geoscience degree, you never have to do a field trip overseas. You never have to take a flight if that's something that's important to you. And every compulsory trip except for the geology trip to Spain, which I think is required, is within the UK. So if that's important to you, you can make a decision that takes that into account. But hopefully, even if you haven't experienced it much before, fieldwork is really, really fun. You get to go out and use instruments, see in the field practical stuff that you've learned about in the classroom being applied. And it's usually really nice. The students all get to know each other. We get to know them better. Most of the time, everybody has a really good time. And the virtual field trips are a really good alternative for anyone who can't do that for any reason. Right, the teaching that we do in the field or out of it is taught by world-leading researchers in their field. Here's some world-leading geochemists teaching about petrology and geochemistry in the field. You're being taught by people who are discovering brand new stuff as it's happening. And what that means is by the time you get to third year, cutting-edge research is being built into the stuff you're learning about. Okay, and what we like to focus on is what's called inquiry-based learning. So we don't just spill information at you. It's about you learning to learn for yourself. Right? We're not just here's a bunch of stuff, go away, memorize it, read a textbook. It's about learning how to learn, and that's a really important skill for the future. If you're interested, we offer a study abroad option. You could take 1 year out and go and study in a partner university in a different place in the world. Doria, who is at the back over there, did this last year. If you have any interest in doing this, go talk to her. She knows how it works and can tell you about what it was like. We also have the Arthur Holmes Society. This is our student-run society, the Geological Society. They run things like student socials, so everybody gets to know each other. They run the department ball every year, which is attended by students and staff, which I'm definitely going to go to next year. First year I was heavily pregnant. Second year I was on field work. Next year is going to be my year. I'm going to get to go. I'm always very disappointed. They also run careers events and things like that to put students in contact with future employers. And that's important because why do you do a degree? Many of you, it might be important about getting a job afterwards. What can you go on to do? Okay, so one thing we really want to emphasize is, as I kind of said already, you could go on to do lots of different things, okay? You have a really useful degree that you're coming out with. We have these transferable skills that I used to think were nonsense, but actually are super useful, okay? You have an understanding of the earth. You can give good presentations. You can understand science and data and how to analyze it. All of those skills are useful and can be used on lots of different graduate programs. You might go on to work for the energy sector, as a geotechnical engineer. You might go on to work for government, policy making. You might go on to be a teacher communicating earth science to the next generation, which is extremely important. You might go on to be a data scientist using the quantitative skills you developed. You might be an exploration geologist or geophysicist, identifying the resources that we need going forward to create the energy transition that we want to see. We need all of these careers for the future, okay? This is really, really important. And I'll make, again, a special plea for geophysics, because most people seem, if they've ever heard of geophysics, associate it with the hydrocarbon industry and think that's the only thing that we do. All the tools that are developed for finding and identifying hydrocarbons in the subsurface are the same tools we now use to do ocean floor monitoring to site new wind farms and to monitor those wind farms once they're in place, and to monitor carbon capture and storage. And our potential employers are asking us for more geophysicists because we don't have enough, right? So it's much more than just that. And in our degrees, we try really hard to prepare you for industry, okay? We work closely with industrial partners to make sure the content of what we're teaching is what they're looking for. And we try and provide you with the skills that you need beyond just the content. And there are a couple of things to highlight that really are relevant to this. One is that you can do a year in industry if you want. You can take a year out of your 3-year degree and spend 1 year working with an industry partner and then come back for your final year. And that's amazing to put on your CV because you can say, I've already got work experience, not just like a summer internship, but a year's worth working in a real company. We also have in 4th year a module called Earth Sciences into Industry, where you work as a group of students and we place you with industrial partners who have real actual problems that they want you to try and have a think about for them and see what solutions you can come up with. And you do that over the course of the year, working with them and each other. Okay, so I have talked to you for a very long time. Now Isabel is going to tell you a little bit about her own experience here as a student, so you can see what it's like from the other side.
I probably am going to repeat everything just very quickly, but at least you know. So why did I choose Durham? I know that most people, you pick your uni based on who's got the best rankings or what the tables are saying. And I know Durham has got a good reputation, but I actually chose Durham because of the college system. If you don't know what the college system is, I definitely recommend asking some of the students because it's a big part of Durham life. So for me, I moved just over 300 miles away from home, so coming to Durham and having this smaller college system really helped me settle into such a big change. Also, because of the college system, you have your own welfare units, you have your own support staff, so the transition is much easier. I also chose Durham because it really does promote a work-life balance. It's not just they expect you to be in the library every day, they encourage you to go and get involved. So I play football 6 times a week, as well as 4 other random sports. So the department in itself, as you've been told, it is quite a small department, which I personally think is really good. I know everyone on my course, if I see them around, everyone says hello, and we all get to know the lecturers really well. The other thing that I think is really good is the open door policy. So if a lecturer is ignoring your emails, you just go and knock on their door and they can't ignore you in person, which is really good. It's also quite good at setting us up for future life. We're not just told stuff and then let into the real world. We are given advice on how to make the best CV for the right industry, scientific writing for when you go, if you go into research. And this year we've also had a talk on internships to try and set you up to get the best opportunities after university. So the course itself, so as you've been told, it's quite flexible between degree paths within your first year, and for me that was quite important because choosing what degree you're going to do for the next 3 years is quite a big decision, and you think it's going to, well, change your whole entire life. Being able to choose a course and then know that if you've decided you've made the wrong decision and you can change it was quite a big weight lifted off your shoulders, knowing that it's not the last decision you ever make. Also quite a big thing is because we have this classroom style learning, it's a smaller jump from school. It's a bit like school. For some people that's what they want, for some people it's not. For me it was brilliant. You're not just sat in a lecture theatre with 400 people, you're not just a number on a piece of paper, you actually are a student and they do know who you are. Fieldwork, that's the best bit about the course really. You get to travel across the UK or abroad, and I don't see why you'd say no to a degree where you can travel to the Alps, Tenerife, California. I feel like that sells it for me personally.